General introduction of earthquake physics, and in particular in theoretical modeling for earthquakes. It requires friction law acting on the fault surface. So to know the friction law of earthquake fault is an essential tool in understanding earthquakes. So for that purpose, we need to know rock friction properties. So there have been many experiments on the frictional properties of rocks. And I showed this figure yesterday, but I'm gonna explain this again very briefly. So this is just a steady state friction coefficient as a function of the slip velocities. Here the unit is meter per second. So at the largest, at the fastest slip, it is almost 1 meter per second, which is as fast as the maximum slip, maximum speed of earthquake fault during earthquakes. So we don't need to investigate this region. So the maximum velocity that we need to investigate is this range. And the lower limit of the slip velocities might be a secular motion of the continental plate or oceanic plate. So this should be the velocity of the plate motion. And this is usually several centimeters per year. Too close? Thank you. So the plate motion is several centimeters per year. That corresponds to 10 to the minus 10th meter per second. So it spans almost 10 orders of magnitude in the slip velocities. But surprisingly, at the lower velocity region, we have a very good phenomenology, or we have a good empirical law that can describe the frictional properties of rocks in a wide range of slip velocities. So this is a subject of today's talk. So we're going to explain what kind of empirical law has been known for this quasi-static slip between two rock interfaces. So during earthquake, this high slip velocities becomes also important, and generally friction decreases very drastically at high velocities. But as you can see, the data are so scattered. We don't have a good phenomenological law for this region. So now geologists and rock experimentalists are working hard to find out empirical laws for this region. But, so I don't explain this high velocity region during this school. So we're gonna see what kind of empirical law has been known for this. So this is a bit older compilation of rock friction experiment. And again, the vertical axis is steady state dynamic friction coefficient. And horizontal axis is slip velocities. in the unit of microns per second. So here it is 1 micron per second, and this is millimeter per second. Usually, if the slip velocities are larger than this, then we could no longer expect the same phenomenology. But in here, we can expect the robust tendency for the behaviors of friction coefficient. This work involves some kind of rock species that I cannot remember now. But the common tendency is that the friction coefficient has a negative tendency, negative dependence with respect to the slip velocities. But the change of the friction coefficient is very small. For example, if the slip velocities increase by 2 orders of magnitude, then the change in the friction coefficient is like second digits, like 0.02 or 0.01. So the dependence is very, very small. And actually, because this horizontal axis is logarithmic and vertical axis is linear, we could see that this is a straight line. So that it means that the steady state friction coefficient as a function of slip velocities can be described by this empirical fitting of the data. Here, this mu star is just a constant that can be regarded as the reference state friction coefficient. And correspondingly, this V star is reference slip velocities. So this just means at slip velocity V star, then steady state friction coefficient is mu star. And the change of the friction coefficient from V star is described by this logarithmic term. So this means, and usually this log means the common logarithm. So if the slip velocity is 10 times larger, then the change of the friction coefficient is just alpha. And usually this alpha is very small. Small, like it becomes, it has only the third digits. And usually this alpha can be either negative or positive, depending on the experimental conditions or the details of rock specimen or composition of minerals. So, so far there is no clear understanding how this alpha is determined. But we can regard this alpha is independent of slip velocities, so that dependence can be regarded as logarithmic. And also, this does not state anything about the absolute value of the steady state friction coefficient. It just describes the change from a reference state. But empirically, in this kind of quasi-static slip, the absolute value of the friction coefficient takes a certain value ranging from 0.6 to 0.8. And that is insensitive to rock species or temperature. Yes. So this is a steady state. And in addition to steady state, we also know the transient behavior of the friction coefficient. And what people did in obtaining this kind of behavior is like this. First, one realizes steady state at some constant slip velocities. Here, the slip velocity is 10 microns per second. And this is the friction coefficient. And it seems like the system reaches a steady state. And after a while, at a certain moment, we change the slip velocity instantaneously. Here, the slip velocity is changed from 10 microns per second to 1 microns per second in a stepwise manner. And right after the velocity change, the friction coefficient decreases like this. Okay.
Is that wrong? An artifact of the way the experiments are performed? Like for instance, when you abruptly change the velocity, it may be that the machine characteristics will not keep up with the...
Exactly, yeah, that's also the very important point. So it generally depends on the stiffness of the machine. And yeah, one can control the stiffness of the machines and found that this jump is not an artifact of the nature of experimental facilities. So this kind of jump is very universal behavior and rock friction. So, and after this sudden change of the friction coefficient, there exists a slow relaxation process towards a new steady state that corresponds to slower slip velocity. And here we reached a new steady state. And next time we change the slip velocity in a stepwise manner. But here we increase the slip velocities from 1 micron per second to 10 micron per second. And again, the friction coefficient shows an instantaneous response. And for this time, this instantaneous response is increasing. While here, the instantaneous response is negative. So if we decrease the slip velocities, the instantaneous response is negative. While increasing the slip velocities, the instantaneous response is positive. And also, after this instantaneous response, we also observe a slow relaxation again. And this experiment is taken from granite with 15 MPa normal stress. But this kind of behavior is essentially the same for other kind of materials like soda, lime, glass, and also acrylic plastic. So we could expect that this kind of transient behaviors is universal, not only for rocks, but can be valid also for glasses or plastic materials. And usually this kind of relaxation process can be regarded as the relaxation time. But in here, the time is not important. Actually, there exists a characteristic length scale over which the friction coefficient relaxes to a new steady state value. So this defines the relaxation length. And in typical experiment, this length scale is on the order of microns. Okay. So this is a typical behavior in transient of the friction coefficient. So we have the transient behavior like this, and also the steady state behavior like this. So combining these two results, we are led to empirical law that can describe both the steady state and transient state. To do this, we're gonna do like this. So first, the friction coefficient is assumed to depend on the slip velocities, and also we need additional variable that is responsible for the transient process. So at steady state, friction coefficient is just a function of the slip velocities. And to describe the transient behavior, we need this additional variable. And this variable is called the state variable, as this is considered to describe the physical state of the frictional surface during the sliding. And in here, we cannot describe the absolute value of the friction coefficient. So we need a reference state which can be taken arbitrarily and describe the friction coefficient as the change from this reference state value. So this reference value for friction coefficient is taken for the steady state friction coefficient at slip velocity v star. And using this reference state value, the friction coefficient at arbitrary state can be described as the change from this reference state. And this change depends on the slip velocity v in a logarithmic term. And also for this state variable, we assume also the logarithmic term. So we have two terms, each of which depends on respectable variables, the slip velocity and the state variable. So these two terms corresponds to this kind of two qualitatively different response. So we have instantaneous response with respect to the change of slip velocities. And this instantaneous change corresponds to the first term, because this is a function of slip velocity. So if we change the slip velocity instantaneously, then also the friction coefficient changes instantaneously. And we know that if we increase the slip velocity, then the instantaneous response of the friction coefficient is also positive. And so we can deduce that this non-dimensional number A is positive. So this is the physical meaning of the first term. And how about this second term? Second term is responsible for this kind of slow relaxation with respect to the slip distance. And this second term describes a change from the peak of the instantaneous response to the new steady state value. And one can also infer that this non-dimensional constant B is positive, but to do this, we gonna see more details about this functional form. So also it is important to note that we introduce some unknown additional variable, the state variable theta. So actually the physical meaning of state variable is not very clear until these days. So for this lecture, I don't give a detailed discussion for the state variables, but at least to describe the friction coefficient empirically, then what we need is just time evolution law for this state variable, so such that this relaxation process of theta can describe this kind of relaxation behavior observed in experiment. So these two equations are just typical or two most popular evolution laws for the state variable. And this is a time derivative of theta, the state variable. And it has a constant term, which is unity here, and decreases linearly with respect to theta. And also the proportional coefficient is V over L. So yeah, this is called the aging law, which could be the oldest evolution law for this state variable. And the second popular law is this form. Yeah, it is. It does not have a constant term, but it has. It is proportional to the slip velocities, but also we have this logarithmic term. So the relaxation term behavior is not a simple exponential behavior in this case. And these two laws have own good points and also some bad points for each. But what is important here is that we have a characteristic length scale, which is denoted by L. And over this length scale, the friction coefficient relaxes to a new steady state. And yes, so this length scale comes into play in a frictional behavior, and it is very important in the earthquake generation process as well. And the steady state value for these state variables is obtained by setting the left-hand side to be 0. So for each case, the steady state is given by L over V, which gives some time constant. Sorry, it is not actually a constant because L is constant and V is just a controllable parameter in experiment. So this depends on the slip velocities. But this L plays more fundamental role, which is considered to be constant. So I'm going to explain the physical meaning in detail, but at this moment, this length constant L has been considered as the typical length of the asperities. And also, I have to explain what is asperities in case you don't know about it. So I'm going to also explain this. So together with this evolution laws, which can be chosen in accordance with what kind of problem we are considering, we are led to an empirical law that can describe the behaviors of friction coefficient, both for steady state and transient state. So we have seen that at a steady state, this state variable takes the value of L over V. So we can insert this value into here and then retain the steady state behavior of friction coefficient in terms of the logarithm of the slip velocities. And here, this proportional coefficient reads A minus B. So depending on the concrete values for A and B, this proportional coefficient can be either negative or positive, depending on the details of rock species or experimental condition. So in the next slides, I'm going to briefly explain the physical meaning of this empirical friction law. To see the physical meaning of this, we're going to introduce first the concept of asperities, which are the patches of the real contact. And to derive this friction law, we need to assume microscopic processes that occur at asperities. Actually, these are thermal activation process. So we need to assume some constitutive laws that arise from atomistic processes. And from this constitutive law, we can derive this empirical law. But for this time, it is only for steady state. For more general case, I'm going to introduce some papers. So probably you already know that nominally flat surface is actually not completely flat, but it's very rough in the scale of microns. Here, just a blow up of the such nominally flat surface. So this unit is microns. So this length is just 5 microns, which is very small. And this is the height of this surface. And which is, and this surface is very rough because it amounts to 100 or even 200 microns if we scan the distance over 10 microns. So this is an example for very rough surfaces. And actually this surface is made by shear fracture. So it is very rare. It is very rough. And this is more flat than this. Because here the horizontal axis is 500 microns, but the change in the height is only 10 to 20 microns. So this surface has been prepared for prepared by shearing two interfaces. So such a rough profile can be wear during the shear. And the third example is the smoothest among these three. But we can still see some roughness on the order of several microns because it is 5 micron. So, but these surfaces seems flat. But if we look at the surface by eyes, so the friction is actually like this. So we prepare two surfaces and let this upside down and then push them each other like this. So by putting these two surfaces into contact, one can obviously see that these surfaces cannot touch completely, but only a small portion of such surfaces are in contact. And in experiment, such real contact area can be directly seen. And such a small portion of the contact area is called the asperity. And here we can do this kind of experiment. We have two transparent rough surfaces and put them into contact. And because this is transparent, we can inject light through this surface. And for real contact area, the light can go through. But for this kind of aperture, the light is diffracted or scattered. So in here we can see a black region, while at asperities it is more bright. Because this scale is 50 microns, so the size of the patch is like 30 microns or something. In this way, we can visualize the asperities, which are the patches of real contact area. And this is not seen in the original coloring. But what we did is like this. First, we prepare this kind of experimental facility and changing the normal stress. And at each normal stress, we take a photo of the real contact area.
It's a deconvoluted image.
Sorry?
In the previous slide, it says it's a deconvoluted image. It's not very clear what exactly is being deconvoluted.
Sorry, I don't remember exactly, but they need some calibration for this kind of light image to.
Fourier analysis of the surface.
Yeah. So at the smallest normal stress, we have less contact. But if we increase the normal stress, we have more and more real contact area. And most of them are surrounding those at lower normal stress. But also we have new asperities by increasing the normal stress. So from here you can see that the real contact area is much smaller than the apparent contact area, at least in this normal stress range. And actually, these people, Dietrich and Kilgore, found that the ratio of the real contact area to the apparent contact area is almost identical to the normal stress applied on the surface, normalized by the yield stress of the materials. So in these graphs, the horizontal axis is the normal stress divided by the yield stress of the material. So they showed 4 materials. This is quartz, calcite, glass, plastic. So for each material, the yield stresses are very different. But by normalizing the normal stress by the yield stress, and the vertical axis is the percentage of the real contact area. And it is almost on the same line, which proves that this relation. So this means that if the normal stress is 1% of the yield stress of the material, then the real contact area is only 1% of the apparent normal area. Yes.
This real contact area, does it change with time?
Exactly. So that is also a very important point in rock friction. So I'm going to come back to this point later. So by using the fact that the normal stress and also shear stress must be supported by these real contact areas, we can write down the formal expression for the friction force as a summation of the shear force at each asperities. So this index I denotes each asperities, and this sigma I is the shear stress on asperity I, and AI is the area of asperity I. So that the area times shear stress defines the force, actually the shear force acting on asperity I. And the total shear force is just a summation of all asperities. So it's a kind of identity here for the friction force. So in general, this shear stress acting on asperities may be different from asperity to asperity. But here we just use the average value for each asperities and write the average value of the shear stress at asperities as sigma y. So this is the average value, and this delta sigma I is the deviation from the average value. So we just rewrite this as this. So, and this is just deformation, and yes. So, if the surface is sufficiently macroscopic, the number of asperities are large. So this fluctuation term, actually the summation of fluctuation is order square root n, where n is the total number of asperities, while this average value is order n. So for sufficiently large surface, we can disregard the second term and can consider only the first term. And also, another reason why we can neglect the second term is that actually this deviation from the mean value is not so large for if we interpret these asperities as the grain boundaries. So of course, in some grain boundaries having lower grain boundary angles, the shear stress could depend on the slip direction relative to the crystallographic orientation. But for most grain boundaries that have a higher angle, such orientation dependence of the shear stress are not so large, and it is more or less isotropic. So that is also another reason why we neglect this. So we proceed with this expression. So the macroscopic friction force can be described by the average shear stress acting at asperities with this summation of the area of asperities. Here we just write A true, and A true is just defines the real contact area. And as the friction coefficient is defined by the friction force divided by the normal force. So by using this, it is written like this. So the numerator, it is average shear stress at asperity. And also the denominator is the normal load divided by the real contact area. So it is regarded as the average normal stress acting on asperities. So this quantity is actually macroscopic quantities, but it is also regarded as the average friction coefficient for each asperities. So in that sense, the detailed nature of the surface topography does not really important in the absolute value of the friction coefficient, but also the average shear stress and actual normal stress at asperities determines the absolute value of macroscopic friction coefficient. So because we have this expression at asperities, if we can assume a realistic constitutive law for each quantities, then we can derive the friction law. So we're going to assume two constitutive laws. The first one is for the shear stress. As I mentioned, this real contact area can be regarded as a kind of grain boundaries. So usually the slip at the grain boundaries can be done with some kind of thermal activation process. But we don't assume a specific process for the grain boundary slip, but just assume this kind of thermal activation law, which involves the activation energy and the temperature, Boltzmann constant, and also activation volume. And V0 is some intrinsic velocity constant, which can be regarded as the order of the sound velocity. So we assume this microscopic constitutive law between the shear stress and slip velocities. This is the first one. And the second one is for the area of asperities. So as Rajit asked, this asperity, the area of asperity is actually time dependent. And this generally it increases as a function of time. And here theta I denotes the time, and actually this is the contact duration of asperity I. So if the contact duration is longer, then the area of asperities is larger. And here C is a non-dimensional constant, which is usually the order of 10 to the minus second in most experiments. So this kind of logarithmic time dependence of the contact area is directly observed in experiment using the transparent materials, as I have shown before.
What material say?
This is glass. And this is time that elapsed from the two surfaces become in contact. So because this is log scale and vertical axis is normal scale, we can see that this relation is logarithmic.
And it should also depend on temperature.
Yes, usually if the temperature is high, then this slope is also high. And usually such temperature dependence is described by constant C. So the constant C may be an...
Is this basically dependent on the mechanical properties? For instance, in the previous slide, we talked about constitutive behavior.
This one?
This one. How mechanical properties change. Could the area of contact be due to that? Just as he was asking, if it is time dependent, is there a viscoplastic component to the mechanical behavior that changes the area of contact?
Yeah, actually this is a very important point. So usually the increase of the asperity area is realized by plastic deformation, because at asperities stresses are concentrated. So this real contact area itself undergoes flow.
Okay, so that means the implication is that the viscoplastic behavior.
Yeah, so to, yeah,
important.
yes.
And that yield strength that you put in, maybe that changes with time.
Yes.
It's not a fixed number.
Maybe there's a viscoplastic
Yeah,
element to
that's
that.
what, yeah, exactly. So the whole thing has to be put in viscoplasticity has to be
Sorry, you were saying which quantity is time dependent?
You had a quantity which was the normal stress divided by the yield strength. So if it is viscoplastic, then that particular thing does not make too much sense.
That's true. So you were saying that because this is time dependent, right?
Yes.
Exactly. Yep. But usually this increase of
Very slow.
very small, very small. Exactly. So this is taken from the real experiment. At this time, the surface comes into contact with no relative slip velocities, so that we can see the real contact area as a function of time. And as time goes by, we see this real contact area increases or spreading around itself like this.
Since you have this picture, I'm wondering if when the actual contact area starts percolating, does anything interesting happen? Because at the moment they are.
We usually do experiments with such area is only 1% of the total area. But if we can do experiment at much higher pressure, then such percolation could be observed. So by using this fact, we can assume that such aging of asperities occurs for sliding asperities as well. And actually this is directly observed for sliding asperities by Dietrich and Kilgore. So we can assume that the real contact area is a function of time with a small non-dimensional number, c. And this time of contact of asperities depends on the slip velocities like this. Here, L is the longitudinal size of the asperities, so that if the top plate is moving at the slip velocity v, then the contact duration of asperity could be like this. So by inserting this here, then we can say that the real contact area is a decreasing function of the slip velocities. And because the real contact area is proportional to the friction force, this means that for faster slip, the friction decreases. So we have some identity here, and also we assume two constitutive laws for real contact area and shear stress. By inserting these two quantities into this, we end up with a microscopic expression for the friction coefficient. And here we introduce a new notation, capital P. And capital T is just a normal load divided by the real contact area. So it's a kind of the average normal stress acting on asperities. So, and E1 is the activity and omega is activation volume at the slipping asperities. And, yes. So this should correspond to the empirical friction law. And by comparing these two items, we can deduce the microscopic expression for these empirical parameters A and B. Although this B still has a new empirical parameter that is responsible for the time dependence of the increase of the contact area. But here we have atomistic constants like activation energy and activation volume and the temperature. And actually, this kind of expression has been known for more than 15 years ago and verified in experiment. Here, the value of A itself can be measured or directly measured in experiment. And also temperature is controlled in experiment. So if we if we measure the value of A by changing the temperature, we can see that this A is roughly proportional to temperature. So that this relation is partially verified. And also by, and this P was the actual normal stress acting on asperities, and it is regarded as the yield stress of the material due to the stress concentration at the asperities. So this is a value for most rocks, 8 gigapascal. Then using this, one can estimate the activation volume, which could be reasonable, or one cannot verify this value because we do not specify the actual atomistic process for slip. But it is not ridiculously large or ridiculously small. But at least we have verified this proportionality between this constant and temperature. And for constant B, unfortunately, we don't have any experimental validation to this state. So this is the this gives the absolute value for the friction coefficient. So if we use this 8 GPa and this activation volume for this value, we can calculate the absolute value for the friction coefficient as a function of the activation energy. And here, the horizontal axis is the activation volume, also the activation energy. And this is the friction coefficient. As I mentioned, the value of friction coefficient is typically around this value for most experiments. And that can be a constraint for the activation energy. So for this expression to give a reasonable value for the friction coefficient, then this activation energy must be within this range, which is around this value. And this is about 150 to 201 kilojoule per mole. And what is interesting is that this activation energy would be insensitive to rock species, and most rock for most rocks, these values are more or less similar. So this is also a very interesting point to investigate the frictional properties from a microscopic viewpoint. So I'm almost running out of time. And, yes. So here we have derived the friction law from a microscopic point of view, but notice that this is only for the steady state. For more general derivation, including the transient state, you can refer to this paper in archive. Okay, it's time, and that's it for today. Yes.
For instance, in metals, when there's two surfaces are subjected to contact and wear is there, sometimes self-welding can occur.
I'm sorry.
Self-welding. Welding between the two surfaces can occur.
That would be at some high temperature. Normal temperatures
Even as long as the outside layer is removed, even at 400, 350, 400 degrees Celsius, metals can get welded. When we talk about the transient behavior stick-slip process, could that be a possible, is that possible in the first place in rocks? Such a self-welding sort of behavior at large pressures?
some melting process that's happening.
Yeah.
Could be.
Need not be melting.
Yeah, but some sticking has to happen. So when is sticking?
Metals, two metal surfaces which are fresh, totally devoid of oxides, will stick to each other. Right? Is there something similar which can happen?
There was interactions among metals.
See, that too we are having huge pressures.
Yeah, usually in rock experiments, we do very thick samples, so that the bending takes a lot of force. So it is unlikely with a sample with that such thickness. And if we do experiments for thin rock, then bending could break the samples because it is very brittle. So to directly observe such bending is difficult in a rock experiment.
When you have asperities, the focal length stress will be very high. And because of that, there can be fresh surfaces that are exposed. And two fresh surfaces, I'm wondering whether they can adhere in
That's it.
Will lubricants change these pictures considerably?
That's true.
Real rocks and some networks of water.
That's true.
What is the
Lubricants may play a very important role, of course, but at least laboratory scale, even if the lubricants are on the surface, but it usually does not affect the detail process at here. But such lubricants or interstitial materials can reduce the normal pressure on the surface. For example, if there is a significant frictional heat produced by the shear, then the water may be vaporized to increase the internal pressure and then reduce the normal stress acting on rocks. So that kind of mechanism is of course hypothesis in real earthquake faults, but some people believe that such process actually happening during earthquakes.